In this video, we're going to discuss two concepts useful in describing heat flow and temperature change. Those concepts are heat capacity and specific heat capacity. So let's start out by introducing the concept of heat capacity. So heat, as we know, is the transfer of thermal energy between two bodies that are at different temperatures. One substance must lose thermal energy and one substance must gain that thermal energy that's being lost. As the substance gains thermal energy, its temperature will typically increase. Well, how much heat can a substance absorb before its temperature increases? Well, that brings us to the definition of heat capacity. Heat capacity is the amount of heat that is required to increase the temperature of an object or a substance by 1 degree Celsius or Kelvin. So for example, let's say we had a 1 kilogram copper frying pan. We put it on a hot stove. The frying pan would begin to absorb heat from the hot stove. The quantity of heat that this pan must absorb in order for the pan's temperature to increase by 1 degree Celsius would give us the heat capacity of this pan. If, for example, we had a 0.5 kilogram copper pan, it would have a heat capacity of half that of the 1 kilogram pan. And if we had a 1 kilogram cast iron pan, it would also have a heat capacity, but that heat capacity would be different than both of the copper pans. So we can calculate heat capacity, which is abbreviated generally with a capital C, as follows. Heat capacity is equal to the quantity of heat divided by the change in temperature. So the quantity of heat that's absorbed divided by the change in temperature, where the change in temp is final minus initial. So that gives us units of joules per degree Celsius, or it can sometimes be joules per Kelvin. So the heat capacity is determined by the type and the amount of substance. So the type, meaning whether the substance is made of copper or iron or aluminum, and the amount of the substance. Is it 1 kilogram, 2 kilograms, etc.? Heat capacity is what we call an extensive property. The value is proportional to the amount of the substance. So extensive properties depend on the amount of substance present. Now we can rearrange the formula for heat capacity in order to allow us to solve for the quantity of heat that is absorbed. So if we know the heat capacity of a substance and we multiply that times the change in temperature of a substance, we can figure out how much heat was absorbed or released by that particular substance. So these are very useful equations, the two that we just looked at. So you want to be sure that you make a note of those and remember them. Now here's maybe an extreme application of heat capacity. Let's say you were designing the heat shields that go onto the bottom of the shuttle. These heat shields, of course, are there to absorb the heat that's generated upon reentry. So if you were designing these heat shields, you would want to design heat tiles that had very, very high heat capacities. So that way, some substances with very high heat capacities, that means that they can absorb a large amount of heat before the temperature of those tiles will increase by 1 degree Celsius. So substances with high heat capacities can absorb a lot of heat before their temperature increases. Substances with or objects with low heat capacities can only absorb small amounts of heat. So very efficient heat capacities will prevent the astronauts from getting cooked essentially upon reentry. So let's take a look at this problem involving heat capacity. A reaction is performed inside a calorimeter. A calorimeter is basically just a large insulated vessel used to perform reactions and study the heat transfer. So we perform a reaction inside a calorimeter. The calorimeter's heat capacity is 478 joules per degree Celsius. How much heat in joules is given off by the reaction if the temperature of the calorimeter increases from 25.1 to 28.9 degrees Celsius? So pause the video and give this problem a try. Okay, so first of all, we're solving for Q. We're solving for how much heat is given off by this reaction. Q is equal to the heat capacity times the change in temp. So we plug in our heat capacity and change in temp, final minus initial. Now remember, when we subtract the temperatures, we get 3.8 degrees Celsius, which is 2 sig figs. We multiply that times 478, which is 3 sig figs. So our final answer is 1,800 joules to 2 sig figs. Now, note that this number here is how much heat was absorbed by the calorimeter, because we're actually measuring the change in temperature of the calorimeter. However, if this is the amount of heat that is absorbed by the calorimeter, then this is also the amount of heat that is released by the reaction, assuming that all the heat that is released is absorbed by the calorimeter. So the 1800 joules is the amount of heat released from the reaction and also the heat absorbed by the calorimeter. Now let's look at our second concept that we want to discuss, which is specific heat capacity. The specific heat capacity, which is often called just specific heat, is the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin. So it's very similar to heat capacity, but here it's always 1 gram of a substance that we're referring to. So unlike heat capacity, specific heat depends only on the type of substance, so whether it's iron or copper or aluminum, but not the amount or mass. So for example, a 1 kilogram copper frying pan and a 0.5 kilogram copper frying pan would have different heat capacities because they have different masses, but they would have the same specific heat because they're both made of the same substance, copper. Now the formula for calculating specific heat, which is generally a lowercase c, is equal to Q, the amount of heat absorbed, divided by the mass of the substance times its change in temp, where the change in temp again is final minus initial. And the units here would be joules divided by gram times degree Celsius or sometimes Kelvin. Now specific heat, as we mentioned, is generally lowercase c, but sometimes you'll hear it, see it given represented with a lowercase s. Specific heat is an intensive property, and that means that the value of the specific heat does not depend on the amount of substance, just the type of substance. Now, similar to heat capacity, we can rearrange this formula to solve for the amount of heat that must be absorbed or released by a substance, and that's equal to specific heat times mass times the change in temp. So again, be sure you're familiar with the formula for specific heat, and you can rearrange it to solve for heat as we did here. So here's just a brief list of some different substances and their specific heat values. So you can see here iron, copper, lead, all these substances have different specific heats. And it doesn't matter how much of a substance you have, its specific heat is always a constant value. So let's take a look at a problem. Again, read through the question, pause the video, and see if you can solve this. Okay, so we have a soda can that has the same specific heat as water. Calculate the amount of heat that's transferred when one can is cooled from 25 to 3 degrees Celsius. So we want to, here we're looking for the amount of heat, which would be Q, and we're given the specific heat we assume it's the same as water. We know the mass of our object and the change in temp, we can figure that out. So if we plug those values in, we should get something like this. Now we want to start out by calculating what's in parentheses, our change in temp. And here, it's always final minus initial. Be careful. Now we get a negative 22 degrees Celsius. Now if we take this and multiply it all out, we get a Q value of negative 32,000 joules or negative 32 kilojoules. Now briefly, this negative sign is very important in thermodynamics when we're studying heat transfer. A negative sign for Q, if we have a negative Q value, that doesn't mean it's less than 0. It simply means that heat is being lost from the system, in this case the soda can, and absorbed by the surroundings. So the negative sign means that our soda can is losing heat, which is indicative of it being cooled from 25 to 3 degrees Celsius. If we had a positive Q, as we did in our previous problem, that means that that substance is absorbing heat. In that case, our calorimeter was absorbing heat. So be sure that you understand the concepts of heat capacity and specific heat, and you can solve problems involving both.